Hopefully this won't be a quick one. Not doing all the time. Yeah, I got ambitious and decided that I was going to try and explain what a monoid was.
Yes.
And then I got to about slide 20. And thought, this isn't yeah, slide 20 and I was somewhere around the end of functor part, and it's like, this isn't a lightning talk anymore. So I thought.
So do we actually get our degree after this?
I was just like, all right, you know what? This is an entire presentation. I'll do another time. Finish another time, and I'll just focus on something small and hopefully useful in the form of monoids. Does anyone here know what a monoid is, or feel comfortable enough to describe what a monoid is? Good. You're the only one I'm going to bore, and you're the only one who can gainsay me as well. Right, so monoids are a lot less scary than monads, and hopefully a lot easier to describe. So obviously they come from the world of maths, I should have warned there's some advanced maths in this. I hope that's okay. So if I was to bring up some maths like this, can you spot a pattern? Same pattern that maybe you can see in this bit of logic here, and same pattern that appears down with these strings. So this has all come, like I said, from the world of maths, and when you get to suitable levels of maths, you stop doing arithmetic and you start trying to spot patterns in the way that things work. And these all follow a very simple pattern. Yeah, they all follow the pattern that they are things of the same type, like we've got a few integers here, some way of combining them, in this case addition, and that results in something of the same type. So that holds true for these other ones here. So as well as the integers and addition, we've got booleans and the logical and strings and concatenation. All these operations, what are you going to say?
So that's which one?
The last one is...
It's missing an S.
Oh, yeah. Pretend that's not there. Like I said, work in progress. Yeah. So, that is a pattern there. And in maths, they call this the closure requirement. And it's useful because you can chain these operations together. And you can also do things like a fold operation across it. And you can sort of chain them together, obviously, because each iteration gives the same type, so you can just keep going with them. So that is the first requirement for being a monoid. The closure requirements. Okay, but there are a couple of others. So let's go for another pattern. Sorry, this maths is getting even more advanced. Got parentheses now. And yeah, the S has appeared. So yeah, there's another pattern here, which is that the order we do pairwise operations in doesn't matter. Whether we add 1 and 2 together or 2 and 3 together first, the result will be the same. So this is also a requirement of closure of a monoid, and this is called the associativity requirement, and that's a lot harder for me to say than I thought it would be. And this is useful because it allows you to parallelize, easy word to start saying, hard word to stop saying, parallelize operations, and also divide and conquer. Those are the obvious ones. But it also leads to another one, incrementalism, which means that you can actually stop doing the operation at any point and continue it again later without having to recalculate everything that came before. So this means you can say if you've got a big document and you're doing a word count and someone then goes and adds another page in, you don't have to go back and recalculate your word count for all the existing stuff. You can just continue where you left off. Oh, yeah. Let's go for another pattern. It's the final one. So this pattern shows, let's see, so we've got 1 plus 0 equals 1, true and false and true both equal, well, true and true equals true, false and true equals false, and hello world string with an empty string added is hello's world again. So, these are interesting because there exists a 0, which when combined in this way, doesn't actually produce a change. And that's called the identity element requirement. And this is useful. It provides a starting point for incrementalism. What do you start with when you incrementalize? You start with the 0 element, the identity element. It's kind of the empty thing. And it allows you to deal with empty cases, such as if you're given an empty list and told sum them, what does it sum? Well, it comes to the identity element, 0, which is one of the differences here, or it is the difference between fold that we saw before, which takes a function, but it also required a seed value, 0, and reduce, which doesn't require a 0 because it can work with the identity elements. In this case, 0, because it's a list of integers, or an array of integers in this case. Yeah. Is everyone with me so far? There's no questions. So
On that last one, where does the law come from then?
So, the naught has come from, as I understand it, because F# understands that in the case of integers, there is a identity element which is 0. So it starts with that already, because it's that. If you have to evaluate it and say, well, okay, I don't have it, so what do I have? In the case of integer, it's 0. In the case, in the case of integers and addition, it's 0. If you were doing something like with strings and you said, well, I want to make a string. Well, what do you want to make it of? Well, I haven't got anything. Then you'd go, okay, so the identity element would be an empty string. It sort of leads into, if we get into computational expressions, you can actually, when you're defining your own ones, you can define what the identity element is, or I think it calls it 0 if you're doing it yourself.
Is that how it works with booleans? Obviously, when you use ORs, obviously the identity element is different for.
Yes, it's different for different operations.
It's based on the operation.
Yes. Yeah, monoids is both a case of the types that you've got and the means of combining them. It's put together. So if I go back to the identity element here, in the case of ANDing together two bools, the identity element is, strangely enough, true, because if you AND true, it doesn't actually have any impact on what the first argument was. You will end up with the initial argument. It's easier to see, obviously, with the empty string. You add an empty string onto a string, you get the original string. I think probably the Boolean ones are the ones which are a little bit more mindfucky, because then there's also, if you do an OR operation, I'm trying to remember what the identity element is for that.
False.
It's false, isn't it? Yeah. Anyway. So, things plus ways to combine them that satisfy closure requirements, associativity requirements, and identity element requirements equals a monoid. I've just got through that so much faster than I thought I would that I might actually go back and do the functors. Is everyone cool with that being a monoid? And monads are, if I go all the way, boom, monads are just monoids in the category of endofunctors. So yeah, what I intended to do, and I'm doing this entire presentation arse backwards because I am going through the slides a lot faster than I thought I would. I was going to define first of all, I was going to put up some humorous quotations because everyone should start off their presentation with some humorous quotations. and then go in and explain what these terms are that you get in this. We've covered monoids. Hopefully they sound pretty straightforward now. Endofunctors. Endofunctors are even easier than monoids. So I've already made the joke about advanced maths, so I'll skip over that and go into functors. So these are functors, which might surprise you if you've never actually looked into what a functor is, to find out, you think that functor would be some sort of crazy transformational function. Actually, functors are types. And what makes these functors is that they are things that can be mapped to other things. So, for instance, an integer, 1, if you add another integer onto it, then you've mapped it to another integer. So through applying a function of addition of 1 to this integer, we've got something else, we've got another integer. Similarly here, booleans, we've done logical AND, that is actually mapped it to another boolean. And hello world, I'm applying the 2 upper from, say, C# there, and I have screwed up that one as well. 2 upper and, yeah, compiler's broken. Right, so functors are pretty straightforward for us. Obviously the term comes from maths, where there are a lot more things than what we cover. But in programming, what we mostly care about are types. And in almost all programming languages, almost all types are functors, because almost all types can be mapped. So that makes things pretty straightforward. So endofunctor. That sounds more complicated. But they're not. It simply means things that can be mapped to other things of the same type. So, in fact, all of the examples we saw before were also endofunctors. So, integers, bools, strings are all endofunctors because they can all be mapped through functions to things of the same type. So, same as with functors, in most programming languages, pretty much all types are also endofunctors. Which means that actually, if you talk about monads, why are we even talking about endofunctors? Because they're not very interesting, why don't we just say types? Well, the functional programming community have settled on a more restrictive definition because endofunctors isn't very helpful, you might as well say all types. So, they have settled on a definition that an endofunctor is a type for which a map function exists. Here are some examples in some languages. I mean, the most common functor that you probably are familiar with are something like an array or a list. If you're coming from JavaScript, since whichever version of JavaScript, you've got the map function. That's hanging off of the array prototype, so it's available. Therefore, an array, since it has a map function, is a functor. F#, got map as well, got list map, array map, option map, everything's got a map. C#, you're probably more familiar with Ienumerable, which obviously is an interface that you can apply to all things lists, arrays, collections of various sorts. And although in this instance, in C# they called it select in link, it's the intent is the same. It's a mapping function. It does the same thing. I think they just went with select because they were trying to make it look a bit like SQL. I don't know if there was a deeper meaning behind it. So, the fact that all of these exist mean, of course, that all these collections are functors in the functional programming sense. Yeah. Oh, and this is the bit which everyone gets wrong. Functors are the types, not the functions that act on them.
Shouldn't they be all tactuals then?
Yeah, it's more like, got employer, employee, function, functor. I think that's what it's meant to be. But because of this confusion, it means that if you go away and you try and actually look up things like what a monad is online, you will find so much disinformation and so many people getting it wrong that it gets really hard to sort of see the truth for what's out there. And that brings me back to where we began, on monoids.
So in a Cody domain, what would be the difference between a functor and an endofunctor?
So, how you're using it. In this instance here, these are all being used as endofunctors.
But if, for example, you mapped it from x integer to a string saying this number isn't x, it would just be a function.
Yeah, it can still be used. Well, the type itself is still an endofunctor. The fact that you're choosing not to use it in that way doesn't invalidate the fact it's still an endofunctor. You're just using it as if it was a functor at that point. So you could kind of say that all endofunctors are functors, but not all functors are endofunctors. It's a more rigid classification. I've really struggled trying to think of an example for this of an functor which wasn't an endofunctor. I don't think any of the programming languages I use actually do have one, at least nothing that springs to mind. So yeah, do people get what endofunctors are now? And monoids are now? So, I suppose what I was also going to mention briefly at the end was what the monoid stuff actually means. Because part of the problem that, say, OO developers have coming to functional programming languages is the lack of, or the perceived lack of, patterns. If you've come from OO, you start getting used to there being design patterns you can apply. And then they get really thrown when they come to functional, certainly I did, that there aren't really any patterns, but there are idioms. And monoids are a programming idiom. They're kind of a whole way of recognizing deeper patterns in how things work, and then using abstractions over that. So with a monoid, say with like integers and addition, we're recognizing that actually adding together a whole bunch of numbers follows a certain pattern, and that allows us to actually abstract up things which are like basically aggregations. We can use that, we can fold, reduce, we can map, and we can do this at a higher level, and it gets us out of that imperative for each loop. So, shit, maybe I should have actually gone for trying for the actual hat trick there and doing monads at the end, because that went really fast. Yeah, are there any questions?
If you have type your own type like a point or something,
Yeah.
you could, combine 2 points and you could have a 0 point, so it's kind of a monoid. But I don't know in F# how you would. Is there a pattern you can implement or not?
Yes,
but,
I should say.
You can derive from it.
So in F#, they've actually baked some stuff into the language that allows you to specify, if you make your own type, you can put some static members on it for things like bind and return and 0 for the identity elements. And then F# allows you to do computational expressions, which rely heavily on things that follow this behavior. Basically, if you make something that follows this behavior, there is a bunch of syntactic sugar in the library. So, for instance, we had the list sum there, or array sum, or whatever, and we saw it work with integers. If you define your own type, and you kind of specify what the addition operation is for it, and what the 0th element is on it, then you can actually pass in a list of that to list sum, and it will do that aggregation for you.
And the way you do that is by going down the computational expression route.
Actually, for list sum, you can just pass it as a list to list sum, and it'll do it. Computation expressions, that one is too big to get into in the last 5 minutes of a lightning talk. But it's, yeah, I did, at the last one I talked about something, I'm trying to remember what, oh yeah, option. I talked about types and built up to, discriminated unions built up to option type. And here I talked about the sort of basic definition of the bits that go towards monads. Because I'm trying to build up to getting everyone up to a level where I can do one on computational expressions without everyone getting completely lost in the syntax and the language. So yeah.
What I had in mind was, like in Haskell, there's type classes for monoid and functor and
Yeah.
duplicative and monoid and stuff, so you can, if you have a type like point, which you don't want to, it might not be a monoid and all that stuff, you can just say it's an instance of monoid when I implement these couple of functions. So you don't have to worry about whether it's a just all those other things. You can just make an instance of that.
So I don't think that F# has like base types that you can extend, or I think it just relies on that things are the right shape. If it has certain static members, it will go, right, based on that, I think these are monoids, and I can do stuff with those.
It's almost like structural typing. So
Yeah.
it's got one of those, and it's got one of those.
Therefore,
this will work.
I can do this because it has the right things that I can call. So yeah, it looks a bit like duck typing. You just put the bits on that you need, and miraculously, suddenly things work with it. A bit more like the way that, say, Go does interfaces, where you just you don't have to implicitly say that it matches this interface. If it has the right things, it matches and it'll work. So that's what I want to build up to and do computational expressions in the future, because they are kind of sexy.
So I think this has been one of the criticisms of F# in the functional programming community, because in languages like Haskell and Scala we can define those types like mono, but in F#, because it uses the .NET type system, you can.
Yeah, it's kind of funny. I do think or feel that with F# they have done everything they possibly can to avoid the M word, right down to basically doing the entire monad kind of idiom thing, but calling it computational expressions. It's like it's monads, but everyone's scared of the word monad, so we're not going to call it that. We're going to invent another term for it. Any other questions? No? Okay, thanks very much.